This is a brief video demonstration of the VOGrid project. On screen now we have the system architecture, and for the purposes of this demonstration we will follow the flow of data. The physical layer has to do with transformer substations. These are medium to low voltage transformers, typically within 400 to 600 kVA. These are distribution transformers in which DSOs or distribution system operators typically have no visibility at all. They have the larger power transformers connected to their SCADA system, but for the most part it is not economical for them at the moment to be monitoring their smaller transformers at the distribution level. This is the gap in the market that the VOGrid project is aiming to solve. We have developed IoT devices that are installed in this physical layer in these transformers, which deliver data via LTE over MQTT to our VO stack, and eventually the outputs of that are delivered to a dashboard and to a SCADA system. To give you a quick sense of what the physical installation looks like, we have here the IoT devices installed with sensors in place for current sensing, temperature sensing, voltage sensing, and other parameters inside of the medium to low voltage transformer substation. We have worked as part of this project with two DSOs. Both of them are based in Denmark. One of them is 34 Elnet and the other is Constant. And we have about 110 of these substations now being monitored, and the data is being delivered into the VO stack from them. The data itself, the purpose of the project has been to develop digital twins of these assets at two levels. The first is a substation level virtual object, which is a digital twin that consolidates all of the parameters, operational parameters in terms of electrical, thermal, and other data into a well-defined virtual object. From here, and in this case, as I mentioned, we have about 110 installations at the moment, so we have that many instances of this virtual object in place. The second layer of this has to be is the composite view of the transformers that fall under the same radial. That is to say, all of the distribution transformers that are supplied by a common power transformer at the medium voltage level. From a DSO perspective, it's important to have both the granular view of the substation, but then also a network level view of what's happening within their network at the radial level. And that's the purpose of the development that we have done here as part of the project. These are, of course, this is the GitHub repository, but we have also deployed this on the Nephele platform. At the moment, there are some issues with the platform, as we have learned from our mentor, but there is a video that has been uploaded to verify that this has in fact been deployed. For demonstration purposes, what we can do here is show you data, live data coming from a few of the substations that we are monitoring. We are monitoring data for the temperature, both at the transformer level and within the enclosure. So that means we install one of our temperature probes directly on the top of the transformer, which is behind this panel, and the other is installed in the upper half of the enclosure so that we have a sense of what the ambient conditions look like. Besides that, we monitor a lot of electrical data, so everything from frequencies, voltages, any unbalanced situations, the total harmonic distortions, what the current levels are both in the phases and in the neutral line. And this is one of the key parameters that the DSOs use on an operational level to understand what the operational conditions of the transformer look like. We look at the loading of the transformer both on a per phase level and aggregated for the overall transformer. And when a DSO is evaluating the health of the transformer, they're basically looking for correlations between the amount of power that it is being delivered and the thermal loading as it occurs. So the thermal response of a transformer tells them a lot about the health of the transformer, which then helps them make decisions both at an operational level and in terms of planning for replacement or upgrade of transformers. So we have now consolidated all of this information. It's visible here in Grafana and is also being delivered through the IEC 104 standard directly into the SCADA system of the DSOs. A major part of the work that we have done has been in terms of the commercial aspect of this type of a solution, and we've worked closely with the DSOs to develop a fairly comprehensive cost-benefit model that would help them evaluate the longer-term viability of this type of a solution. And the result, it turns out, is very positive. So in gray here, we have a number of assumptions that have been validated in collaboration with the DSOs. And considering the cost of the solution, we can see that the return on investment is quite strong, and the DSOs are therefore very interested in expanding this to their broader networks. So that is a brief summary of the work that has been accomplished as part of the VOGrid project. And we do expect that it will, after the project is complete, that this will become a commercial solution that the DSOs will be adopting. Thank you very much.